Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show, bringing you another really fascinating guest today who's involved in creating a better tomorrow for many people out there. Today, we have the honor of being joined by Dr. Renée Deehan, who currently is the Vice President of Science and Artificial Intelligence at InsideTracker. And she's involved in leading a science team that ultimately builds and helps mine the world's largest data set of blood, DNA, fitness tracking, and phenotypic data from healthy people, ultimately to create evidence-based solutions for customers that are simple, that are clear, and ultimately actionable. Dr. Deehan spent her career working in this precision medicine and personalized nutrition domain, as she previously served as the VP of Computational Biology and Translational Informatics at QuartzBio, also as the VP of Biology and Bioinformatics at PatientsLikeMe, which is the world's largest integrative community of health management and real-world data platform. At PatientsLikeMe, Dr. Deehan was responsible for data and knowledge engineering, artificial intelligence and machine learning, and ultimately translational biology functions, helping to drive infrastructure and consumer and business product development. She was the principal investigator for the DigitalMe Ignite program, which was involved in collecting longitudinal blood and patient-gathered health data from over 5,000 at-home site visits from over 2,000 participants, and was able to generate a couple million data points through that program. She's been involved in designing and then cross-functionally implementing a variety of first-generation research platforms, again, capable of integrating both survey data as well as omics data for a variety of biomarker analysis. And really, been involved in this fascinating intersection of what we refer to as the omics, bringing together proteomics, methylomics, metabolomics, and a range of other important areas of biomedical data to, as you say, really perform actionable insights. She has her PhD in molecular and cell biology from University of California, Berkeley. She did her bachelor's in bioengineering down the street here at University of Pennsylvania. And we're lucky to have her with us today. Dr. Renée Deehan, thanks so much for taking the time to join us on the show.
Wow, thank you very much for having me. I am absolutely honored to be one of your many esteemed guests that I have seen. So thank you.
Yeah, well, I really appreciate you, Renée, taking the time to come talk to us today about everything you have going on, because it really is a very exciting segment of everything that's happening in biotech as we're on the cusp of 2023 here. I would love to start off, though, as we typically do, by handing you the floor for a little bit, just to talk a little bit more about you, so we can get to know you a little bit beyond the bio that I just read, a little bit about your background, everything from where you grew up, the development of some of these intellectual interests in bioengineering and molecular and cell biology, and a little bit of those early days of your career journey. I think that'd be a great way to start things off.
Cool. Awesome. Well, I am currently located in Cambridge. I was born in the Boston area in Newton. So, but as you mentioned, I went off to college in Pennsylvania. Go Quakers. And that's where I did end up majoring in bioengineering. And I was just thinking about this the other day. I still regret, I think I should have double majored in biology and computer science, because I think ultimately that ended up being, kind of what I do. But as I'm sure is the same for you and many of the folks in our field is, you're just sort of born a nerd and absolutely curious about anything. And, I was thinking the other day too, I was like, why am I not a quantum biologist? Like, that's where the action is. I mean, but I can literally be interested in most things because everything is absolutely fascinating. And the majority of my industry work has been focused on networks, and that's we're living in a social network. But we are always constantly in harmony with our environments, whether that's, a cell in a greater tissue or whether it's like a person in an office building. It's just, I think about these interdependencies a lot, but I loved biology, so I did end up majoring in bioengineering, which at the time, which was the late 90s, I would say that bioengineering at the undergraduate level was like a sampler platter of engineering. So you just really get a little from columns A, B, C, D, and E. And at the same time, I was working in a worm lab doing worm genetics with Elizabeth Bucher, and I loved it. I had a great time. And I wanted to continue that laboratory work. So that's why I spent, really the next 7 years between a tech position and graduate school, very focused on molecular biology and cell biology, which is funny because I actually have not taken very many molecular cell biology classes. But during that period of time was kind of the early genomics revolution, right? With DNA sequencing and microarrays came on the scene. And I remember seeing experiments that people were doing, and they would measure, all of a sudden you could just measure 1,000 things in one experiment, right? And they would pick maybe 2 of the most interesting things to them, and they would just deeply characterize those in an experiment. And I just wanted to characterize the other, 998 interesting things that were there as well. So I'd say that's what really ended up leading me into where I've spent the majority of my industry career, which is I think could be fairly described as computational biology, which is a hugely, multidisciplinary field where you need to have subject matter expertise in the development and implementation of different methods that you apply to large scale data sets, but you also have to have real subject matter expertise in biology as well. I feel like that's almost like the overlooked part in bioinformatics and computational biology, as everybody thinks it's like very math intensive, but you need that subject matter expertise to understand the myriad of edge cases that exist out there that you always have to account for. So that's how I moved through kind of the educational component of my life and into industry.
Excellent. Yeah, it's I really enjoy sort of the convergent sort of bridge themes here, and when I have guests like you that, as you were saying, here's biology exciting, computer science exciting, but when you put them together, the synergies that pop out are just, really have the potential to change a lot of what's happening. And Renée, I really, I enjoy when I do these shows, sort of going into the sort of the peer-reviewed literature and taking a little journey to see sort of where you've been after you came out of university, what I'll call sort of in this case pre-InsideTracker time, and clearly, what I ran into, highlights, why you're so perfect at what you're doing now, and we'll get into that in a little bit. But some of what I ran into was just so ahead of its time, in the sense that, I pulled up papers where you were basically looking at, say, pharmacogenomics in this particular case of looking at anti-TNF therapy in rheumatoid arthritis and trying to understand, sort of the cohort of patients that was not responding to these really novel, cutting-edge biologics. Another area that you published several papers on, you call it different things. At one point, you refer to it as 21st century toxicology. Another, you call it toxopanomics, which I know sort of the term toxicogenomics. I was like, yeah, but this is much more than that. Where I think actually you were working for doing some research for a tobacco company at the time, but really looking at things like across the spectrum of DNA damage, cell death, cell senescence, and really understanding sort of the complexity of what goes on in that particular case. Cellular damage from certain metabolites and so forth. Talk a little bit about this era, the sort of this Dr. Deehan era, because I think what you're doing here, obviously, it makes us understand why you're doing what you're doing now in InsideTracker. But take us through a little bit of this period, if you would.
Yeah, awesome. I love that. I love that you picked up on those, those papers in particular. And I would say, both of that exploration all started at this company called Genstruct, which later branded as Solventa. And I spent the decade after graduate school there. And, interestingly, it was there where I met Gil Blander, who went on to found InsideTracker, and my predecessor in this position, Milena George, I met her there as well. Also Dexter Pratt, who I don't know if he would technically be called, I consider him, really, he was the architect of the platform that we built at Solventa to actually analyze all of this omics data. And again, this was back in 2006, and microarrays were all the rage. RNA-seq wasn't really here yet, but what Solventa had developed, Genstruct back then, was a really beautiful, elegant platform whereby you could take the thousands of measurements that you might get from an RNA experiment and make inferences, causal inferences, to say, what happened to cause this pattern of gene expression that I see, right? So essentially, you might say, in the case of TNF, which is the target of many drugs in rheumatoid arthritis, but it's, it's essentially in the growth factor category. It's very pleiotropic. You can put it on cells and you can do a microarray experiment or an RNA-seq experiment and really get a signature for RNA expression. And what the platform that we had built it allowed you to do was really make some informed guesses about what were the different molecular players that occurred in between that cell engaging with this, potential drug target, and then very downstream where you see signatures in gene expression. So what this allowed us to do is to take a lot of published information that was out there and assemble that all together in one causal network knowledge assembly model. And Dexter Pratt was our head of knowledge modeling. And what I learned about there was the ability to take decades worth of research, extract the most salient results from those research papers, transform that into a computable, machine-readable format, and then put it all together, just like we do with databases or like a relational database. We were doing that with results, with knowledge. So, data might be that my LDL cholesterol level is 134. But in inference or knowledge might be that individuals with elevated LDL tend to have a higher risk of myocardial infarcts over the next 5 years, or whatever it is, right? That's the data is the measurement itself, but the knowledge is like, what do you do? What do you do with that information? What can you say about it? It has a lot of context. And so we were building knowledge bases, but we were using those knowledge bases to help us understand what these large scale data sets were telling us. Because when you measure 1,000 things in an experiment, what you can't do is just mentally go through every single gene in the experiment and say, oh, is it up or down? What does this mean? Let me Google every single paper there is about LDL and heart disease. And you know, we can only keep so much in our tiny human brains. So that's where I really learned how to teach computers how to think like biologists. And I mean, we're far from being able to really do that, right? We're still smarter than the computers. But that's where we started. What is it like? What does it mean to interpret this data? What do we have to do? And how can we create a system that does that for us? So anyway, the two papers that you mentioned were awesome, and they were very different in that one I'd say was very knowledge driven and another one was very data driven, but both were this mix of knowledge and data. And the first one, the work that we did with the tobacco company, it was Philip Morris. And this was work that was led by Julia Hong and Manuel Peich at Philip Morris. Yeah, and they really, we worked together on a very large strategy that they had in order to evaluate the biological impact of products, right, for systems toxicology purposes. And what they wanted to do was essentially characterize not only what the overall impact of a product might be, but what molecularly was the impact of that given product. So you could compare, say, a standard reference cigarette against a vaping mechanism, right? And say, okay, well, overall, how many genes does this perturb? And then take it a step further and say, okay, well, specifically in terms of the autophagy pathway or the cell senescence pathway or the DNA damage pathways, which genes do we think are, you know, kind of perturbing those pathways, and in which direction do we think those pathways are going? So this was part of a very large scale strategy whereby we were building knowledge models like these networks, like you might see in a KEGG diagram or like figure 6 of a review, these kind of signaling molecule pathways. So we would build these networks that described everything that we knew about senescence in lung cells, or everything we knew about senescence in heart cells. And then we would augment those models with experiments that were in relevant cell types and things like that. And then we would test them with kind of obviously a held out data set and say, okay, well, how much of all the data that do we see in this experiment where they, you know, activated a senescent pathway, how much of that is actually covered by the model that we built? With the overall goal of being able to use that model to then compare what is the impact of product 1, 2, 3, 4, 5 on senescence. But that was part of a much larger network biology schema. And so it was, you know, I think I was talking to somebody the other day about digital twins. It was very much a digital twin, like very, very much a digital twin, where you build something using knowledge, you augment it over and over again using data. It kind of learns from the data that you feed into the system. The model is improved, but then you use that model to then, you know, test something that you can't test necessarily in a real world population, which we can. I mean, we'll know the answer in 20 years, but the goal was to try to create more of an in silico approach or a lab-based approach to start to tease out what was going on before the 20-year mark.
Absolutely. Yeah, I thought that one specifically extremely elegant. I mean, I'm going to come back to it a little later on when we get into sort of nutrigenomics or nutripanomics, I guess we can, but you know, if we substitute, you know, the tobacco for X, Y, and Z interventions. But yeah, we'll come back to that. But I really thought that was extremely elegant. Again, I wanted to lay the groundwork for people listening and watching to sort of everything you were doing beforehand, and to the audience, go out and, you know, go into PubMed and check out Dr. Deehan's publications, because they are pretty cool. Let's segue now to InsideTracker. You know, you have the role of vice president of both science and artificial intelligence, and you know, obviously a very broad spectrum of programs here. I was wondering if you could sort of walk us through just a little bit about the background of the company. I mentioned, you know, a little bit about its founding, and a little bit about, if you would, I mean, because I see sort of, you know, the advertisements, and I downloaded one of the white papers, and we'll get to the longevity in a little bit. A little bit about sort of where all this amazing data comes from nowadays, because obviously thinking out there to the population of everybody in the world, you know, obviously there's certain people out there, like I guess my father and mother-in-law, that, you know, may have one set, you know, they go to the doctor and they have the other blood test. There may be someone like me who's a little more of a biohacker. And then there's, you know, sort of more of the advanced biohacking folks. And we all might have different sets of data, different types of data. Talk a little bit about sort of how all that feeds into the InsideTracker system today. I'd love to understand a little more how it all works.
Sure, and I will do the best that I can to give you some of the history. I have, of course, known about InsideTracker since its inception, 12 to 14 years ago, really quite some time. And of course, Gil and I worked together back in the Genstruct days, and you know, he left and then went on to found InsideTracker. So I had definitely, you know, he and I would always catch up, you know, at least once a year, and always had a really good eye on it. And then when I actually went to PatientsLikeMe, I think in a way, conceptually, the two companies were doing something very similar at heart, although very, very different. InsideTracker is exclusively at this time focused on well individuals, in that you know, there's no recommendations about drugs that you might want to take or anything like that. But really what the product is you come in, we measure things about you, right? And these measurements can come from blood-based measurements. Now we have the ability to also incorporate physio trackers, so anything that you might get from a wearable, as well as DNA. And then, of course, we do ask individuals questions about themselves. So we'll say user-generated health data. So all of that kind of makes up your health profile at a given point in time. And then that is coupled with the, you know, AI part of the system. And the AI part really kind of has two, I call it like two halves of the brain. I call it like the observer half and the sage half. And if we just start with the sage half, that's really where InsideTracker was started, where they curated recommendations for lifestyle interventions. And so this is where the science part comes in. A lifestyle-based intervention in this case would be a nutritional intervention, a supplement, an exercise intervention, a meditation type of wellness intervention, but something where you didn't need a prescription and you could really kind of take control all on your own. You don't need anybody's permission or anything like that. And those two elements were coupled, the measurement of who you are and what your health state is right now, together with recommendations that are science-backed and made by experts. And so, you know, if we take the example of LDL, maybe somebody with a profile of elevated LDL would be interested in taking some of these recommendations. And so the scientists at InsideTracker literally did meta-analyses for things that may improve your LDL for, let's say, maybe women between 40 and 50 with an elevated LDL of X to Y, right? And so they would read all of these articles about, okay, well, what is the influence of consuming flax meal on LDL? And, you know, if there was a sufficient amount of evidence that suggested that there might be a benefit here, and the elegance with which the system was built, that the scientists do these meta-analyses and they curate all of this information is, I mean, it's just, it's outstanding. It is beautiful. It is part of the reason why I came here. But, you know, they take into account, of course, how many people were in the study. What did the study look like? What was the intervention exactly? How long was the intervention for? What was the outcome? Was the outcome statistically significant? What journal was it published in? And then overall, they might look and say, okay, out of all of the papers that looked at LDL and flax meal, how many of them had a positive result or a negative result? Or it was inconclusive and they couldn't even say it was either way, right? And then if there is a preponderance of evidence, then they'll say, okay, you know, it looks like flax meal for some people may really move the needle here. So that is something that could be then pushed to the product. So just imagine that on a grand scale for many different biomarkers and for many different types of lifestyle interventions. And really that's what the knowledge-driven, I call it the SAGE part of the platform is you can take your biomarkers and then filter that through all of these, you know, lifestyle-based recommendations that really have been investigated by a bunch of people sitting in a room and reading papers and curating them manually. So there's the other element of the platform too, which I would call the observer part, and that's more the data-driven part. And that might be something like, oh, okay, so it's really interesting. You, well, how about this example? This is your LDL level. What's everybody else's LDL level across this population? Like, how are you doing, Renee, for somebody with your characteristics?
Yep.
Or, wow, you've really been exercising for quite a bit. Like, have we actually seen your resting heart rate go down? Let's see. So these are the types of things that we're working on now, more analytics focused, to bring more of a data-driven element into the product.
Excellent. I don't know if I got an email or what, maybe I just, because I was going through the site, but I downloaded the longevity biomarkers white paper that's available for anyone that wants it. And I went back to my most recent doctor visit. So my CRP, HbA1c, and LDL were fine. My triglycerides a little high. My vitamin D low. And here we have sort of this initial set of longevity biomarkers. And as you were just saying, right, there's potentially lots of them out there. You got some great thought leaders in terms of Lenny Guarente, you got David Sinclair and others. Talk a little bit about longevity. I mean, this is a very hot topic for us, not just sort of longevity, but this whole concept of this burgeoning concept of health span. And then, clearly, again, sort of going back to the previous work that I pointed out in terms of the toxopanomics, each of those categories, when you think about DNA damage and autophagy and senescence, there's a whole other sort of network of biomarkers behind all that stuff as well. Where do you see this potentially all going? Obviously, there's a lot of knowledge that can be, using your tools, your scientific knowledge, but also your AI, and we'll get to that in a bit. Talk a little bit about where you see things going on the health span longevity front with these tools.
Yeah, that is a great question. And I am going to be hopefully a good scientist and point out the caveat that I am not a longevity expert. As you have probably seen, I've actually spent the majority of my career in healthcare, not to say that diseases of aging are, not part of this equation. But, compared to Gil or certainly Lenny Guarente or any of those folks, I am trying to my best to catch up, although trust me, I have opinions. But in terms of, I love and hate the term health span. I love it because I understand what is meant by it. The reason that I shouldn't say I hate it, I don't hate it at all. What I really want to do, and I feel like I read a nice piece by, it might have been Matt Caberline about this, is I would really like to turn this into a clinical definition, right? Like, let's all decide what health span actually means, right? Because I think we all want to improve it, but if we don't have a definition of it, we can't measure it. If we can't measure it, we actually have no idea if we're improving it. I would say, though, that directionally, we can certainly figure out what is good for us versus bad for us in a lot of cases. Take something like, we know that exercise is really good for us, right? So I don't think I need a clinical definition of health span to tell me that if I do 45 to 90 minutes of zone 2 training 3 times a week, good things are going to happen for me. Like, great things are going to happen for me, not only in the kind of short acute term, but also, in the preventative long term, right? I will improve insulin sensitivity. Will probably, I might lose weight. I will become a more efficient fat burner, all of these types of things. So we think a lot about this. And actually currently we're working on different ways to encourage people to create and keep habits that will allow them to improve health span, or at least do things that we know are good for you and should extend health span, right? So we've been thinking a lot about what is the smallest, tiniest thing that you could do for yourself today, once a day, once a day. What is that one tiny thing, right? Like, it's 10 p.m. Have you done that one tiny thing for yourself today? If not, like, what is that one tiny thing? It doesn't even have to be that big. You forgot to take your supplement or eat that flax meal or something like that. Go do that. Go do a 20-minute walk around the block, get outside for a little bit, 5 minutes of meditation. Doesn't really matter. Pick your favorite thing. Whatever is entry level for you is awesome. So we've been thinking a lot about that, because I think it's to me, it's interchanged with preventative medicine in a big way. And I feel like we've not, as a society, been able to crack preventative medicine. Maybe it's because it's a capitalist society and it's hard to spend money there. I don't know, but I am very excited about that. And my hope is that these changes will lead to increased health span once we are actually able to quantify what it is. And certainly InsideTracker is very, very much interested in that. We have an algorithm that is a blood-based inner-age algorithm right now that'll give you your biological age. And we're looking at ways to, in the next version of that, expand it so it can also include, relevant physiomarkers or maybe even other functional markers that are, relevant from a clinical perspective or have clinical meaning. That's very important to me, especially coming from the background that I have, which is analyzing a lot of research grade multi-omic data. It is hard to translate that into, even I'll say clinical action, even meaning wellness-based types of interventions. So one of the things that I really like very much about InsideTracker is the things that we are measuring have clinical relevance, right? We know that ApoB, which will be measured, is tied to cardiac risk, right? We know that HbA1c levels are associated with risk of diabetes and insulin sensitivity, right? So we know that VO2 max is another great measure of cardiometabolic health. So, it's not like random obscure protein on a proteomics panel and we don't really know what it does or who it binds to. And there's not a 30, 50-year body of research behind it. I can walk into my doctor's office and hand them this sheet of things and they understand what the vast majority of them are. So.
I totally agree with you about health span, by the way. I like the term youth span. Well, at least when I survey sort of the my mother and father-in-law that are close to 90, they laugh when I say health span. They're like, no thanks, we don't want to be a little healthier, we want to be younger. But that's a totally different thing. But when it comes to random obscure protein that you were just saying on the panel or biomarker, whatever it is, let's segue a little bit to the AI part of this, because clearly this is another extremely hot area, and we've delved into AI beyond healthcare on the show in all different fields. Clearly, with what you're doing, as you say, okay, if you have one biomarker, fine. If you have, for instance, this these 5 longevity biomarkers, okay, things get a little more complex. But clearly, as these weird proteins on the panel start pouring in, you need the AI tools, you need the machine learning. Talk a little bit about your own experience with, obviously, you have all the cellular molecular biology work, the AI has come on the scene. Talk a little bit about your own sort of, getting up to speed process with some of these new tools, because they're evolving as we're talking right now, and a little bit about how you see things ultimately, moving towards again, using these tools for, once again, development of knowledge and not just crunching some data.
No, it is a great question. And I honestly think in the biomedical space, this is broadly, I would include pharma, biotech, wellness companies, all in this. Unless it's something like imaging and assisting pathologists with making calls on, is this skin cancer or not? Or, I think just like classic machine learning is actually quite developed for that particular application. I think it's hard. It's going to be hard to take all of that omics data and hope to just toss it into a machine learning model and get something reasonable out that is going to be applicable in a real world setting. And the reason why I think that is because we are very good at measuring a lot of things in a few people, right?
Yeah.
So oftentimes, just from a very practical standpoint, when we have been approached to, let's say, build a class, we'll take the rheumatoid arthritis paper as an example. And in this paper, what we were trying to do is build a classifier to predict which rheumatoid arthritis patients would respond to anti-TNF therapy versus not, for many good reasons, like it's a progressive disease and only 50% of people respond. And then you might just go on another anti-TNF and you may not respond to that one either. And now it's like 9 months later. So, in that case, you may be measuring, you may have, maybe in our training set, we had 200 individuals, and a microarray experiment at the time was like 15 to 20,000 genes. And at that point, you have an overtraining problem. You will absolutely build a classifier that will work. There's no question about it. Just because it's the same multiple testing problem as you have in a statistical model. So one of the ways you can solve that problem, of course, is to not throw 15,000 things into the model. And there's a lot of really great techniques to figure out how to shave that number down to 200 or something that is a reasonable number to use. And always the way in which I have liked to, and others have liked to approach this problem, is to use knowledge, is to use prior knowledge to help reduce that number of measurements down to something that actually makes a lot of sense. And in that particular paper, what we did was, I'd call it feature compression, where we took those 15,000 things and compressed it down to, I think, 1,500 features.
Okay.
But each of these features represented a biological signaling molecule. It represented, let's just say, on the order of 50 to a couple of hundred different genes, and was really a summary score of the pathway activity of those 50 to 150 genes. So it would be very functionally related. For example, if you wanted to use TNF as a feature, then I think we had like 250 different genes that we knew could be regulated by TNF. We knew the direction of TNF regulation, like if you added TNF to cells, would this gene go up or down? And then we were able to say, okay, well, in, you versus me, what do those 250 genes look like? And when you sum them all up, is Ira's TNF higher than Renée's, or is Renée's TNF higher than Ira's? And that's the way that we got from, in that case, 250 down to 1. But we had to use a lot of knowledge in order to collect, to even be able to do that. So a lot of words just to say, I think that we are getting quite developed at building machine learning pipelines. Okay. And you can, use various different programming language to pull in these different pipelines. They will be point and click soon if they're not already. I have no idea, where you can build your own machine learning model in an hour. And that is wonderful. But I think the harder part is really the interpretation of that. And the interpretation of that does mean that you need to build knowledge bases. And I think it's the knowledge base, for example, that InsideTracker uses is all of those papers that all of the dietitians and exercise physiologists and subject matter experts had to read and then extract the results from to make a conclusion that was then stored somewhere, right? So, if we did that meta-analysis for LDL and flax meal, the impact of flax meal on LDL levels, maybe they read 15 papers, maybe only 10 of them were relevant. But those 10, all of the information from that was curated and stored somewhere, and it still lives there, even if that happened 10 years ago, and it will still live there 10 years from now. So it's not like Renee spent the weekend doing a meta-analysis. I wrote down my conclusion and then I walked away and it's gone. So I think it's just very important that we have ways of harnessing decades of research and like billions of research dollars. Like, how do we make that useful? It's just sitting out there in PubMed.
Right.
But I think so. I think the answer is not just data and math. I think that interpretation comes from priors, and priors live in that colossal body of published literature. And I think the people that are going after that published literature and trying to make it useful are going to be a step ahead of the game, because you don't hear very much about that type of AI. It's still artificial intelligence. It's more in the general AI category, right? It's expert knowledge systems. It's knowledge representation and reasoning. It's recommendation engines. All of that is artificial intelligence. It's just not machine learning. And so I think the folks that are really kind of working at the nexus of that have kind of figured it out, and they're taking the next step. I mean, you come from a developmental background, right? Which I think is awesome, right? Like, I think that like that voice, I want to hear more of that voice in this world. But I think about cell fates and how complex that is, you know, that tree of decisions that an organism is making as it develops. Who can hold all of that in their heads? Like, that is a knowledge network. Just that fate, you know, that whole model of fate is a knowledge network.
Absolutely.
So if that can be used with data, maybe it can inform what's happening with your data intelligently.
No, it's a very elegant way to look at it. Yeah, no, it's spot on, actually. Yeah, I mean, I appreciate that perspective. Right. A couple months ago, you were interviewed in for this article in NutraIngredients magazine, and you had some really interesting quotes in there, both on the themes of, as you're saying, the complexity of biology, but also personalization. You know, talking about, you know, what I think we all do. These sort of people that have hung out in this industry long enough, you know, you would love to see at some point a move away from sort of the one size fits all single magic bullet approach that has been, you know, it's yielded great blockbuster drugs and made a handful of companies extremely rich. But at the end of the day, we are an extremely diverse, complex set of folks out here. And whether we're talking about pharmacogenomics or nutrigenomics or whatever, you know, sort of the omics thing is, at the end of the day, where do you think all this is? I mean, where would you like to see this all go in 5-10 years? What would you ultimately like to see sort of InsideTracker, you know, 10.0 at some point be able to do, whether it is, parsing out, you know, specific things in terms of, repurposing of drugs, or, you know, specific diet insights, and, I should eat more cucumbers, you should eat more asparagus, and so forth and so on, because it really goes in so many directions. Talk a little bit about what you see in the years to come with some of these tools.
Yeah, that's a great question. And I can definitely tell you what I would want if I personally had my druthers, especially with respect to InsideTracker. I mean, I think, like you said, we've been in the field a long time. We know what personalized medicine means. We've even started to do some of it. But that is really the function of InsideTracker's platform. It's no different from personalized medicine, right? If we think about food or meditation or exercise, they're all interventions, right? So, which is like just it's actually very different for me, coming from a healthcare background, because I can like test this stuff on myself, right? Like I am the candidate person who likes to do these types of things. I can try something and then evaluate and see whether it works or not. So that's the holy grail, because like you said, it's not the same. It's not the same for everybody. I can't even conceive of going on a ketogenic diet. My body rejects high levels of protein. Like I just don't like it. I don't crave it every once in a while when I do, but I know I should eat more protein and all of this, but it's one of those things where I just know that it's probably not how it is just something in me that says I need to eat carbs every day.
Me too.
Or I get a headache, or I feel faint, or, and who knows? I am so far from a dietitian. Maybe there's great reasons for this and I should just try it otherwise. But, I think the point is that maybe that's my body telling me that I actually need this as a fuel source. So what I like about InsideTracker is it can acknowledge something like that. It can acknowledge what my diet is, and it can acknowledge where I am today, because it might be very different from where I was 2 months ago. 2 months ago, I ran in a long race and I had my blood done and my, CRP was just through the roof, right? There was a good reason for it.
Right.
So maybe at that time, my protein needs were different than where they are right now. Maybe during a period of intense stress where my cortisol is spiking, my recovery needs are different than where they are when I'm, in maybe a more stable period in life. So that's what I like, is that I in a future state, I want to see the product be able to keep up with where I am on an increasingly rapid pace, right? Or at an increased cadence. So it's not just every couple of months when I get a blood draw. Now we have physio data. So now I can track how my sleep is going every single day. I can, start to understand maybe how my meal timing is influencing my sleep every day. I can start to understand, I can, get more rapid feedback. So in a future state for InsideTracker, I am the type of person that I kind of want to be told what to do. I have decision fatigue, right? Like I would love to really be nudged to go to bed at the appropriate time at night. I would love to have food that is nutritious and catered to me just up here without really having to do very much. I would love to be reminded to eat when I need to and reminded not to when I don't, because I have like a 1 a.m. cheese and crackers problem, which is recommended by absolutely nobody. But I would love to be cheered on for all the little things that I do better today that I didn't do so hot on yesterday, even if it's not eating cheese and crackers at 1 o'clock in the morning, right? Like that's an improvement for me.
Sure.
May not be your problem, but I want that, like in my dream world, that is the level of personalization. That would be amazing. And, of course, with all of that, I should see concomitant changes in these biomarkers that we care so very much about that have, are tied to function. So I should see my lipids decrease. I should see my blood sugar decrease in HbA1c. I should be able to maintain, good like ferritin iron homeostasis. I should be able to, when I get sick, be able to recover reasonably well because my immune system is robust, right? That's what I want to see. But I also love that we're just able to measure more things now than we used to be able to measure, right? And I can't wait for those omics measurements to trickle their way more into the clinical domain. Sure. Which, by the way, I'm seeing them. I just was looking at a test from Castle Biosciences for it was a diagnostic to look at the metastatic potential of a particular uveal melanoma.
Okay.
And it was RNA expression based. And I was like, this is so cool, right? Like, this is so cool. We were trying to build this stuff like 15 years ago, and now it's here and it's like being used by doctors, and people can make real treatment decisions that are based on RNA-seq. Like, awesome. Progress has been made. So how do we do more of that? How do we get that out faster? How do we get like the FDA to keep up with the pace of everything? Those are more meta questions. But I think for longevity and for wellness-based interventions, I mean, the sky is the limit. It's beautiful over here, right? Yep. People are just more interested in quantifying themselves than ever.
Absolutely. Absolutely. And obviously, if this is confidential, just tell me we can't talk about that now. But any plans in terms of companion, in this case, companion food products, functional foods, nutraceuticals, anything that we can expect to see from InsideTracker? Obviously, you talked about the flax meal a lot in terms of the LDLs and all that stuff, but stuff coming in the future that, you may pair up whether it's your own consumer packaged goods to service companion products to the InsideTracker app, or potential partnerships with consumer packaged good companies that maybe synergies there between product and app.
I think those are amazing questions. I don't think I'm the right person to answer them. I don't think it's a confidential thing, but more like I'm not sure that I'm the right person.
We'll do another episode then. Don't worry about it.
I know. Well, what I will say is that, and this is, it's definitely, and actually, I don't know if when you were mentioning the white paper, if you were talking about the one that was in Scientific Reports from 2018, but during that year, there was a paper that was published on the InsideTracker data asset. And at that time, we were looking at about 1,000 individuals that had at least 2 blood draws, right? Because we were looking at longitudinal data over time. And, at this point, we have I think almost 20 times that amount of data. And we are also able to track people's adherence to a recommendation, should they choose to track this information, right? So I talk about the flax meal and LDL a lot because I actually have this recommendation, and my LDL is indeed elevated, and I'm trying to get it down with flax meal, among other things.
I better try it myself.
I know. Actually, I was talking to somebody on the team, and they were like, just put it on anything. And I'm like, you're right. I put it on pizza. I literally put it on everything. I kind of like it. It doesn't taste like much, but little nutty. Yeah. As far as interventions go, I mean, this is why I'm actually fascinated by which recommendations do people actually take, because what's easy for me, I leave now flax meal on my kitchen counter and I dump it on things. That's how I do that. But if the intervention is too onerous or it takes too much schlepping, right, I'm less likely to do it. So I think the behavioral aspect of this is really fascinating.
Sure. Yeah.
But what I really, what we're looking to do is to update that paper now that the data asset has grown as much as it has, and see okay, well, do the original correlations between biomarkers still remain? And now that we can track adherence, can we say something more specific, even in a retrospective fashion? Okay, all right, for all the people that did start consuming flax meal, did it work? Did it work in our population? Did Renée's LDL actually improve or not? How can we contribute to scientific knowledge through exploration of our own data set, and how people behave with it? So one of the things that I would love to be able to do is eventually get to a prospective study where you would be able to say, okay, does this actual intervention of an app work? Yeah. And if this intervention of an app works, can we be very specific and say there are certain recommendations that we make that are rather successful? Are there others that are less successful? Why? I mean, that to me would be incredible. And if I think about being able to really prove that a digital solution like this has a place in preventative medicine, that's the type of thinking that we need to do. You really want to perform the RCT on it. But with that said, like you said before, what do you do about the personalization aspects of it? I always think about this one patient in this, it was a gynecological cancer that I looked at, and everybody in that cohort should have died. And there was this one woman, it was 5 years later, and she was still alive. And, you know, I think the study met its primary endpoint anyway, but nobody was talking about this woman, right? Like, you don't come back from the type of cancer that she had, and she did. And that to me is wild, because I'm like, what was going on with her? All of our eggs should be in that, you know, we should put just as much effort into studying her as the rest of the population, all of the non-responders. But to have such a crazy response in that one individual, what can she teach us about everybody else, right? So what I like about this job and what I like about InsideTracker is being able to combine both that like large scale global population level research, but also that I want to see the crazy responders. Like, I want to go snuffle them out and find what were you doing? What was your environment like? What's going on with you that we're not capturing that we should be capturing? Like, I love both sides of that coin. And I think both are really important for this, our field, as we move forward, because it's not a one size fits all. But
yeah, and I love those types of cases too. And yeah, I've run into them as well in other areas, in rheumatology actually. And yeah, to be able to do that deep dive and understand sort of those outliers, I think is where a lot of important knowledge is going to come from. So I really enjoy some of these areas, Renee. I just and it's fascinating just hearing you talk about them, as with myself not being a scientist, but hearing from someone like you and this way of looking at it. So now this is awesome. What else is happening, Renee? Anything we should know about for, as we get close to 2023 here, things happening with InsideTracker that I have not touched on, conferences that you're going to be presenting at, places that we can listen to you, potentially meet you, anything else that I did not touch on, please take the floor and let us know about it.
Oh, sure. Let's see. Conferences are a great question, and that's something that is on my plate to figure out, because I would love to, especially now that the world is a little more open, get out there. I've been at InsideTracker since last February, so I haven't been here very long, and I've been pretty heads down, trying to learn what I can about everything. But I would say I'm pretty ready to, start getting out there and going to some of these longevity conferences, and in particular, really, really interested in fitness trackers, or just trackers in general, because, how much time do we have to enter in data into our, like, we already spend enough time on the phone. So what can be collected if you're comfortable with it? What can be passively collected, and how can we use that information? I would say that's going to be a big focus for the science and AI team in 2023, is figuring out how we can use passively collected data from trackers. Thinking, I'm going to call it like the year of statistics, the year of statistical error. I am really interested in, when we do have a change in a biomarker, how do we know that it is meaningful, right? Like, get really rigorous about that. I was even just looking at my bloods from Mass General, and I'm like, where are the error bars? Like, where are the error bars on this graph? So, thinking a lot about that. But the other thing too is thinking a lot about our data assets. Something that's really important to me and a lot of other folks at InsideTracker is what are the biases in our data set?
Yeah.
Right? There are biases in every single data set. And there's other like really beautiful data sets out there like NHANES and UK Biobank that we can also gather like blood-based, DNA-based information from healthy individuals and sometimes less healthy individuals. And what are the biases? Because is everybody white? Is everybody rich? Is, everybody male? How do we make sure that we can't always fix the biases, but the first step is being aware of them. And that's, of course, really important, especially when you're doing data-driven learning. So yep. I think we're going to, kind of take a hard look at that moving forward, just to be able to characterize what we have. I think we're really interested in understanding how race is used in medicine appropriately, but mostly inappropriately. But, also figuring out better ways to engage with our users. Like, how do we give back information to them in a way that's consumable and engaging and makes them, feel good about the progress that they made in between blood draws or with their tracker over time. And so those for our team are definitely up there. You can look forward to seeing work on women's health, which is a big area, adding new biomarkers, adding new physiomarkers, of course. So those would be in more of the immediate term, and definitely more work on the genomic side, because we're able to add DNA. And so actually I don't want to tease that one too much, but I'm super excited about the application of different methodologies like Mendelian randomization that our genomics team has worked on. And I think there's a lot that we'll be able to add there. So I'm pretty psyched about the year ahead. How people can reach me, I am not that I can be found somewhere. I think we'll see if Twitter dies. But fascinating conversation for another day. But I'm on Twitter as Renée Deehan. I'm on LinkedIn. And I love to chat with people, so you can reach out there, certainly by email as well.
Awesome. Yeah, we will put your socials in the bio of the show when it goes live. And I mean, it's really an awesome set of programs, Renée, that you have in front of you. And I think that we have future episodes to do here as these different modules evolve, and it's just rooting you on as InsideTracker continues to grow and moves forward with its mission. So really great stuff. For everybody again that's going to be listening to this episode of our show across the various podcast networks or watching on the YouTube channel, you've been listening to Dr. Renée Deehan, Vice President, Science and Artificial Intelligence at InsideTracker, doing really amazing things to create evidence-based, actionable solutions for folks to improve their health and wellness. Renée, I want to thank you for taking the time out of your schedule to come talk to us and educate us on these themes. Obviously, thank you for everything that you're doing there to move the science forward. And as we like to say on our show, thanks for helping to create a better tomorrow for people via what you're doing. Really great story.
Absolutely my pleasure. Thank you so much for having me.